Okay, today we are jumping into a really cool sonic mystery. We're going to uncover the physics behind that weird, pulsating wah-wah sound. You know what I'm talking about? Let's get into it.
You have definitely heard this before. Think about a guitarist tuning their strings, right? Or maybe two singers who are trying to hit the exact same note, but one is just a little bit flat. You get this throbbing, pulsating sound that kind of seems to come out of nowhere. So what on earth is that?
Well, it's not a glitch, and your ears aren't playing tricks on you. It's a totally real, totally predictable physics phenomenon, and it's called beats. And by the time we're done here, you're going to understand exactly how it works. So to crack this case, we first need to get to know our key suspects, the waves themselves.
To figure out what's going on when two sound waves meet up, we first got to understand the basic properties of a single wave. Think of these as, the vital stats on our suspect's profile. There are three big ones we need to lock down. First up, we've got amplitude. And really, this is just how big the wave is. It's the measurement from its center line all the way up to its highest peak. When we're talking about sound, amplitude is what we hear as volume or loudness. So a bigger amplitude, a louder sound. Simple as that.
Next on the list is frequency. This is all about how fast the wave is vibrating, how many full cycles it completes every single second. We measure this in hertz, and for sound, our brain interprets frequency as pitch. So a high-frequency wave gives us a high note, and a low-frequency wave gives us a low note. This one is a really crucial clue in our mystery.
And last but not least, we have our trickiest suspect, phase. Now, phase is more than just where a wave is at any given moment. It's also about which way it's going. Is it on its way up or on its way down? It's the whole picture. The easiest way to think about it is just as the wave's timing. To make this super clear, imagine two people jogging. When they're in phase, their steps are perfectly matched up. They hit their high point at the same time, their low point at the same time. They're totally in sync. But when they're out of phase, one person is at the top of their stride just as the other is at the bottom. They're moving in perfect opposition to each other.
Okay, we've got our suspects profiled. We know about their amplitude, their frequency, and their phase. So now, let's see what happens when they actually collide. This brings us to a really fundamental rule of the universe, and it's called the principle of superposition.
Now that sounds way more complicated than it is. The idea is actually beautiful and simple. When two waves are in the same place at the same time, you just add them together. That's it. If their peaks line up, they get bigger. If a peak from one lines up with a valley from the other, they subtract, getting smaller. Or they might even cancel each other out completely.
Okay, so let's use this principle. What happens if you take two waves that are completely identical, same amplitude, same frequency, and you smash them together? Well, as we just learned, it all comes down to their phase, right? Their timing. And there are two big, extreme results you can get.
So first, let's say the waves are perfectly in phase. Their peaks are lining up with peaks, and their troughs are lining up with troughs. They're basically helping each other out. They add together and create a brand new wave that's got double the amplitude. We call this constructive interference. And in the world of sound, that means it gets a whole lot louder. But what if they're perfectly out of phase? Well, then the peak of one wave meets the trough, or the valley, of the other. They are perfect opposites. And when you add them together, they completely cancel each other out. You're left with nothing. Zero amplitude. This is destructive interference. And for sound, this means silence. Okay, we've got all the pieces now. We know about amplitude, frequency, and phase. And we know about superposition. We are finally ready to solve the mystery of that wah, wah, wah sound. Let's put it all together. This is the big reveal. So here is the absolute key to the whole thing. We're not talking about identical frequencies anymore. What if you have two waves that are really close, but just slightly different? Let's say one is vibrating at 380 hertz, and the other is just a bit faster at 384 hertz. What happens then? Well, because their frequencies aren't a perfect match, one wave is always moving just a tiny bit faster than the other. This means they can't stay locked together in sync. Instead, they are constantly and predictably drifting. They go from being perfectly in phase to perfectly out of phase and then right back into phase again, over and over. And it's this continuous drift that creates the cycle we actually hear. So the waves start in phase, right? Their amplitudes add up, constructive interference, and we hear a loud sound. But then as they drift apart, they become perfectly out of phase. Their amplitudes cancel out, destructive interference, and for a moment it gets quiet.
And then, of course, they keep drifting until they're back in phase again, and the sound gets loud once more.
And there it is. That's the solution to the mystery. The wah-wah-wah sound is just our brain interpreting this super fast, repeating pattern of loud and soft. It's the sound of constructive and destructive interference happening over and over again. It's this incredible sonic illusion created by two real sounds adding and subtracting in the air before they even get to our ears.
And the physics behind this is just so wonderfully elegant. The number of beats you hear per second, the beat frequency, is just the difference between the two frequencies you started with. It's simple subtraction. So if you have one wave at 380 hertz and another at 384 hertz, you're going to hear 4 wahs or 4 beats every single second. How cool is that?
So, case closed, right? But you know, every good detective story has a deeper layer. We know what beats are, but it kind of makes you wonder, why do waves even happen? What's the fundamental motion behind all of this?
I mean, why do particles, whether they're in a guitar string or just in the air, why do they oscillate back and forth to create waves at all? What is the most basic fundamental motion that's underneath everything we've been talking about?
The answer is a concept called simple harmonic motion, or SHM for short. And it is, without a doubt, the most fundamental kind of vibration in the entire universe. It just describes any situation where an object is pulled back towards a center point, and that pull gets stronger the farther away it gets. The classic examples are a mass bouncing on a spring or a pendulum swinging back and forth.
This simple back and forth dance is basically the source code for almost every wave you can imagine. The particles in the air carrying sound to your ears, the atoms vibrating inside a crystal, they're all doing some version of this fundamental dance. It's the engine that literally powers the world of vibrations. So, we started this whole journey with a simple wah-wah sound, and we've ended up at the fundamental motion that kind of governs our physical reality. It really makes you wonder, doesn't it, if just adding 2 simple waves can create such a fascinating, intricate pattern. What other hidden rhythms and secret harmonies are out there just waiting for us to discover them, all playing out according to the universe's simple, elegant rules?